Hi everyone, welcome to lecture seminar series. Again, we have a very exciting speaker today and he has a huge profile, so I'm just gonna run over some of the highlights from his career. He currently leads WPI Academic and Corporate Engagement Group. He also regularly served as an adjunct professor in WPI's Boise Business School. He has 40 years of professional experience. He is basically a veteran. Over 30 years of career experience have been in the electric and gas utility business. 7 years of them as a corporate executive at Fortune 500 companies, including Eversource. Mike joined WPI as a director of power systems in 2012. He has his bachelor's from WPI also in 1978. He has a master's degree from Rensselaer Polytechnic Institute and also MBA from the same school, and he graduated in 1987. And today this veteran is going to talk about the energy industry, the power industry, the opportunities, impacts, and some of the challenges. So without wasting much time, let's get started.
And I'm really looking forward to today. I think this is a great course. I really think it's a wonderful thing for you all to kind of explore frontiers in electrical engineering. There's so many ways society relies on electricity these days, and being part of that future is just outstanding. So let me call up my presentation here and share it. Let's see. Share screen. So here's the presentation, and as we said, we'll share the slides. So you can take notes as you like, but you don't really need to. You'll see this later. So this is a bit of an introduction, and Professor Mughal has already covered these things. Yep, I'm old. And I've done a lot of things, but really, I think out of school, I did a few years working at Pratt & Whitney Aircraft as a structural designer, because I graduated as a civil engineer, and did mechanical, and then switched to power plants. And power plants are very large machines that we rely on, and the ones I worked at a wide variety of different technologies, but most of my time was spent in a nuclear plant down in Connecticut, Millstone Nuclear Power Station. And that was fascinating. And as I rose in the leadership ranks, you end up being in charge of more and more things, and I was in charge ultimately of all the projects that we were doing, all the changes. And then I moved over to energy delivery, and that's rose up to be a vice president in charge of engineering at the company. The company was Northeast Utilities in my day. Nowadays, that's part of Eversource Energy. So it's a big electric company. It's the biggest one here in New England. And this is my a little bit about credentials, a few degrees, and registered professional engineer in Connecticut, although I stopped paying the fees, so I can't use the stamp. But there it is. So that's by way of introduction. Enough about me. So I wanted to ask you all a few questions. So perhaps you could raise your hands. I can see you, at least half of you. And I'd say, please raise your hands if you want a career that maybe makes positive contributions to society every day. Okay, I see one hand. I see some holdouts. Maybe there's a few. Oh, that's you, Professor. No. So I'd say, yeah, okay. And how about if you want to transform the world to a more sustainable future over the course of your career? Yeah, that looks pretty good. I think there's some alignment to that. And maybe on a personal level, a career where you can learn and grow, as I did for 30 plus years in the industry. How about high income and job security? Is that a value? Yeah, I think so. So I would offer to you that you should think about a career in the power industry. This is where I spent my career, most of it. I mean, I'm here at WPI for 8 years, so not all, and a few years at Pratt & Whitney Aircraft, but the rest, and yeah, that's the rest equals 30 plus years, was in the power industry. And I thought it was an outstanding place to have a career because it delivered all of the above. It's hard to believe, I think, at times for society at large, that you're making a positive contribution every day. But as soon as you get a big widespread outage and we're into restoration, people know they're counting on you, and you know they're counting on you to get the lights back on. And so the delivery of electricity is so fundamental in so many ways to our society these days. So with that in mind, I thought today what we would talk about is a little bit about the power industry. What is it? Maybe some of its current challenges, maybe some technical opportunities. You know, the power industry is over 100 years old. It really isn't mature. Are there any opportunities left? And preview, yes, there are tons of opportunities left. So here's the outline for today. Just the overview. We'll look at energy in the U.S., career opportunity, and then I thought we'd kind of bridge over and take a more focused look at green energy. And within green energy, I want to focus on electric energy efficiency. And so there's technical content in today's presentation as well. So there's kind of a broad kind of view of things and a discussion about careers, but then it gets down and we get into numbers and we get into energy delivery. So this is a question for the class. Please raise your hand and let me know what is the power industry, and maybe share a definition. Well, I got a lot of hands on the last questions.
I got a mic, so I don't need to carry the microphone, so you can talk and he would hear.
Oh, I see a hand. Yeah, over there toward the back on the end. Yeah. Power industry. So my volume isn't too good. So Professor Mughal, maybe you could repeat that?
Yeah, so he's talking about saying power industry is something that delivers power to consumer industrial sectors.
Oh, beautiful, beautiful. I think, now, was that student reading ahead and looking at this slide? I don't know. But direct hit. Yeah, generates, transmits, distributes, and sells electric power. So there's the power plants making electricity, and what's exciting these days is so-called utility scale solar, which is very large solar arrays. You've probably seen them on the highways. National Grid has a bunch of them along Interstate 90 around near Worcester. Transmits, so in the electric system, there's really two pieces. One piece is called transmission, and that's the really high towers that I have over here on the right. They're really high because the voltage is really high. The voltage on that line is probably 345,000 volts, right? And you all know that volts is kind of a linear scale, and the voltage in the wall socket's 120. So 120 versus 345,000, way, way higher. And that's why the tower is so high and why the conductors are so separated, is so that you won't get a flashover, because those conductors are just bare metal wires. There's no insulation on those, not like our extension cords where, you know, the hazard's controlled by the insulation. In those, the hazard's controlled by the distance and the height. And so that's the transmission system, and that's the part people call the grid. It's like a superhighway system for power, and it's interconnected all around the United States, actually all around each of the world's continents except Africa. I shouldn't leave out Antarctica. So Antarctica and Africa, not so much, but everybody else has a power grid transmission. And the reason you do that is if at the power plant, you can use a transformer and you can really raise the voltage up. And then you can move more power, right? Because the power is volts, electric potential times current, right? Amps, volt amps is the power. And so the power is, if you can raise the voltage, you need fewer amps. Amps is the part that generates waste heat. And so at the higher voltages, you can move power and have lower losses. So that's why the general design is bring the level of voltage way up, move it far distances, and then it lands in these substations shown in this slide, about the center, down near the bottom a little bit, says substation. And this is kind of, each town in the United States will have a few of these. And the transmission system will deliver power to transformers, and the voltage will be stepped down for distribution. Now the poles aren't so high. These are the poles along all the roadsides, you know, out in Anytown, USA, and off to houses. And so these are operating somewhere between as low as 4,160 volts, 4160 volts, and all the way up sometimes as high as 34,500 volts. So those are not, the towers are not as tall. We don't have to, you know, spread the conductors as much. And that'll move electricity. And in this illustration, they're showing two substations. So there's kind of a transmission, a sub-transmission, and then a substation. And then from there comes the pole top transformer on all those poles where power is stepped down to utilization voltage, or 120, 240 volts for use in houses, and maybe a little higher for the farm shown there. So that's the system as it existed, as designed, and it's still in use today. This is the system. Many components of the system are over 100 years old. One of the early transmission lines was built from Niagara Falls, New York, in upstate New York. That same line is still in service today, and I think it's over 100 years old. That's one of National Grid's facilities. Also in this picture, I mentioned power plants, so I put a couple there. There's a power plant with very large cooling towers, right? So these are ways to reduce the temperature of the condensate on a steam cycle, and do that we're using very little water. So that's why those cooling towers are built. And that doesn't mean it's a nuclear plant. It could be pretty much any kind of power plant will do that. And then underneath that is a very large turbine generator set. That kind of looks like the ones I worked on at Millstone. I worked at a plant that generated 900 megawatts electric. And so a pretty big turbine generator set in that turbine hall. Okay, another question for the class here. How's the power industry transforming the world to a more sustainable future? Class? Question?
Saying, trying to make sure that the power is more affordable.
Making it more affordable? Yep, that's a direction. And I think another one might be customer-owned generation, accommodating houses having solar, right? We see that all over the countryside now, and building wind power and integrating that into the existing grid. So we're seeing windmills more and more, and we won't see them, I don't think, because they'll be so far offshore. But the plan is to really build out offshore wind here in this part of the United States, the northeastern part. So I thought we should take a look now, and so I'm going to segue over, and the slides have this internet address, this URL for people, but let me just switch over to that document, that PDF that I'm talking about. Let's look at the energy picture in the US. Okay. So we're kind of fortunate here in the US to have the Energy Information Agency. That's what that web address, eia.gov. And they do a wonderful job of compiling statistics year after year, putting them together, and then putting them in an illustration where we can all kind of understand what the statistics are saying to us. And so this is a picture. It's kind of an interesting picture in my mind, because on the left, there's...
Mike, if you're trying to share something, we don't see it.
Thank you for pausing me. Let's see. Go back over here. I am trying to share something. There it is. There it is. There it is. Okay. How about now?
Yes.
Sorry about that. Okay. So on this chart from the Energy Information Agency shows us sources on the left and uses on the right. And what it's showing us is where is the energy coming from that's used in the US? And this is on an annual basis. So this is 2019, where'd the energy come from? And it's measured in quadrillions of British thermal units, or BTUs, a lot of energy, each one. And so if you look at the top there, we're still getting most of our energy in the US from petroleum. And if you look adjacent to that petroleum block, it says percent of sources. And what it shows is that 70% of the petroleum is being used in transportation. And of course, that makes sense, right? It's turned into gasoline, and we use it for gasoline-powered cars, right? So, and then if you look on the right, you see transportation is the biggest single energy user of the sectors they're showing. They divide all the energy use into transportation, industry, residential, and commercial. And it shows that transportation is the biggest single user of energy in the US these days, and that 91% of the transportation energy is coming from petroleum. So I think this is kind of interesting because I think it illustrates. Now you might say, well, what about electricity? Well, electricity is a transitional form of energy, right? We convert a fuel into electricity, and then that electricity is used in these same end uses: transportation, industrial, residential, commercial, right? And so if you look at where does the electricity come from, where is it getting its fuel? Well, I'd say let's focus in, we can focus on natural gas, and we see that electricity is fueled by 1% of the petroleum used in the US, almost none. 36% of the natural gas used in the US, that's kind of interesting. How about this? 56% of all the renewable energy is converted into electricity. And still, electricity is using coal. And while it's not a big component of the total amount of electricity, it is 90% of the coal is still going to electricity. So when the US burns coal, it's almost always going to electricity. And 100% of the nuclear is going to electricity. So all of those fuels make electricity, which in turn has significant losses. Look at that. 2/3 of that energy is turned into heat. It's losses. And that's what we're going to focus on later in this presentation. And then if you look on the right, where's that electricity going? Well, it's going to commercial applications. So here I like to think about pizza shops. So if you think about a pizza shop and those ovens, those are electric ovens. And so commercial industry gets about 49% of its power from electricity. And in a similar way, houses use a considerable amount of electricity, 41%. Some goes into industry and almost none goes into transportation, right? We're talking about electric vehicles. We're starting to build electric vehicles, but so far it's kind of a drop in the bucket of the total energy picture. Let me pause here because I think this is important. Are there any questions about this? Sure.
Why does the right side not add up to 100%?
Professor Mughal, could you repeat the question, please?
He's saying why the right side does not add up to 100%. Which one?
Oh, yeah, it's not a percent chart. I think it's a quadrillions of BTU chart. So on the left side, we have the fuels and how many BTUs of fuel go in. And on the end use side, we have of the 100 that went in, 76 came out. But look down here at electricity, and you'll see that of 100, first, 37 quadrillions of BTU were converted into electricity. 2/3 of that amount was lost as heat, right? And so 2/3 of 37, roughly 25. And you see that the total amount of fuel coming out over here on the right side is we've lost 25 quadrillion BTUs in the exchange in and out of electricity. So that's where the difference went. Now, I don't think this chart's entirely fair because there's also losses in the end uses over here on these end users. So while it doesn't show the losses in transportation, an internal combustion engine operates at something like 10% efficiency, and about 90% is waste heat. So of that transportation amount, if we could get more efficient there, we could save a lot of energy. But in this chart, it implies that it's all totally used over there. It sort of is, right? It went to transportation, but the gasoline in the tank doesn't actually get me where I want to go, right? It's the car. I need to burn the gasoline. And when I do that, when I burn fuels in any kind of Carnot type cycle, I'm going to lose like 2/3 of the energy to heat, to just waste heat. And that's what the cars do. And so you end up with significant losses in these sub areas over here. This is why an electric car, even after suffering all those system losses here, this 2/3 loss, an electric car can still deliver better efficiency, total efficiency, than a gas-powered car, because the battery motor combination is so much more efficient than the internal combustion engine. Great question. Other questions? So this is the energy big picture, and we'll share this. And I'll stop sharing, go back to the presentation. Let's go back over here. Oops. Once again, I forgot to share screen first. Okay. Share screen. And we'll pick up the presentation again. Okay. Sorry to start again at the beginning. I managed to do that by closing the file before I switched. Okay, so we've looked at the overall energy picture, and we see that the power industry is where we're getting, where about half, a little over half of the renewable sources are going. And so if we want to grow renewable energy usage in the United States, it's quite likely that the way to do that is to convert it into electricity and then use that electricity to a greater degree on those end use applications. So as a result, this desire to move to renewable sources and have a more sustainable world, it is totally transforming the power industry, because the power industry was working fine without that, right? It was burning. When I started in the power, well, we'll get into that. I'll get into that in a minute. But the power grid is being modernized so that these renewable sources can be used and can be used to electrify transportation. And space heating is the primary use there in the residential commercial area. That's just maintaining buildings either warm or cool to the liking of the occupants. And if we want to reduce greenhouse gas emissions, we're going to need to increase our use of electricity. And so this slide kind of shows the IEEE's version of a smart grid. And it's not really fair any longer on the left there. It says, here's today's electricity and tomorrow's choices. Well, we're transitional right now. The grid that we have today, at least in this part of the United States, it still is mostly like the left, where large power plants make most of the power and deliver it, transmission to distribution to customers. That's the original model. That's still in use today. It's still predominant. But on the right, more and more and more, we're seeing things like, if you look on the right toward the top there, you'll see there's a car, and it's an electric car. And so that's a use that we didn't have much of until recently. So more and more electric cars are being built. And as the states have aggressive goals to move toward renewable power and reduce emissions, we'll see more electric cars. Well, that kind of only works, or it doesn't work too well if the power plants are burning coal, so we'll talk about that. And it works much better if we're using windmills, which is why the northeastern United states are moving in a major way toward offshore wind. Very large power generation of wind. It'll be like those, it'll operate like those central power plants, the ones with smoke coming out of them. And if combined with some sort of storage, and maybe the storage is the batteries in the cars, it'll feed power, new renewable, sustainable power, to allow us to electrify the transportation sector. And that is ongoing right now. Any questions on this slide? Okay, hearing none. Let's move on. Now, we said we'd talk about careers a little bit. So let's say, okay, let me ask this. What do you think the career opportunities are given this situation? And let's limit this to career opportunities for engineers, for electrical engineers in the power industry. What do you think? Professor Mughal, could you please repeat the question?
Yeah, he said improving the structure, the infrastructure.
Oh, absolutely. Improving the infrastructure. Yeah, and that's been going on in a major way. And there's even not shown on the slide are things like power electronics, SATCOMs, to allow the transmission system to move more power. So there's loss reduction for the delivery system. Yeah, that infrastructure. And there's also infrastructure to support an electrical vehicle future, right? If we're moving to electric vehicles in a major way, and certainly California recently said, hey, you can only sell electric vehicles in California after I think it's 2030, it might be 2035, but only electric vehicles will be sold. And I've served on the Massachusetts Greenhouse Gas Reduction Committee, and the roadmap for Massachusetts is very similar. It really moved to electric vehicles in a major way. And so that's going to require infrastructure, and that's new infrastructure is going to require engineers, no question. Good answer. Any other answers?
Increasing the efficiency of the power production.
Beautiful answer. Yes, yes. And that's going to continue and go on and on and on. There's the efficiency aspect and also the whole move toward renewables. Well, windmills have been with mankind, for hundreds and hundreds of years. You see pictures of the West, go West, young man, United States of the 1800s, and they'd have a windmill powering a pump, right, to get water. And so windmills have been around. You look at Holland and the windmills going back hundreds of years. But it's these offshore windmills are not like the windmills from back then. They're talking about machines that do 15 megawatts of output. It is fantastic. These are huge machines with windmill blades that rival the height of the Empire State Building or the Eiffel Tower. Very, very substantial structures. And the goal is to increase the efficiency of those. Further, solar efficiency has been improving steadily for a long time. There's a solar learning curve, and it's been making great strides. But I think there's great strides yet to be made in solar, improving the efficiency of it, especially for transient things like clouds moving by, which can really lower the efficiency of a solar array. There's techniques to maybe manage that. Professor Mughal, would you like to say anything about that?
Yeah, I was actually wondering about something, Mike, and this is actually not related to what what we're discussing right now, but before you got started, we were talking about the energy consumption in US by sources, and you showed the slide. It was roughly around 11%, right? And I've been seeing this number close to that for last 5 years. What are the hindrance in terms of for this renewable technology, in terms of the adaptability or government policies or pricing? Why that number is not increasing?
So let's see. First off, not really. Well, we'll get into it. I'll pause that question and I'll answer a little further into the presentation, if I may.
Okay.
So let's see. The other thing I wanted to do here, though, let's see, grid modernization, yep, infrastructure. And I also wanted to share with the students this website down here. BLS.gov stands for Bureau of Labor Statistics. And I think students would be well advised to know about this website as well. So let me go back and go share this one now. And the URL I have on the slide brings you here. And what I wanted people to see is that you can look up things like, okay, in summary, what do electrical engineers do? Okay, well, that's kind of high level. You probably already know that if you're in this class. But what does it pay? Well, that's kind of interesting. If you look over here, as of May 2019, the Bureau of Labor Statistics says that the median annual wage, so median means half the people make more than that, half the people make less than that. And of course, this is all for wage earners. So this isn't all people, it's all wage earners. But the median in the United States as of May 2019 was about $40,000 a year. And engineers do better than that at $94,500. Electrical engineers do better still. Electrical electronics, even higher. This top one says except computer, and do you know why that is? It's because the computer science majors make even more than that. It's so this is a nice website to go look at different futures and think about what you might be able to go and do and what it might pay and so on. And what I liked about this particular slide and why, or this particular web page and why I wanted to include it today was things like design new ways to use electrical power to develop or improve products. Direct the manufacturer and installation and testing of equipment. Investigate complaints. This is a big part of the job at the electric company, is investigating complaints and then fixing things when things break. So, what should we do about this? So it's been a wonderful career for me working on these sorts of problems. So I wanted to just share that with everybody briefly, and I'd encourage you to take a look at that as time permits. So let me go back over here now. Oops.
So Mike, I have a question.
Sure.
How is the work-life balance in the power industry?
Yeah, that's a good question. So it's an interesting industry in that because it's so widespread across the countryside, the employers need to trust their employees. And so you have a lot of on your own time. And it's expected that if there's not widespread customer outages, that people will go ahead and maybe integrate their life. And if there's any errands need doing, well, yeah, sure, it's accepted that you're going to do the errands while you're doing your work. Or if need be and you need to be at home, you can be at home. If for me, I have two children, a daughter and a son. They're in their 30s now, but when they were in high school, they ran track and cross country. I was able to make just about every meet. So in that sense, there's a very forgiving, open attitude. It's expected to do these things as long as your work gets done. Okay, so that's one mode. Then there's the other mode. The other mode is there is a widespread outage, and now it's all hands on deck. And no work-life balance, Professor Mughal, it's work balance. You're going to do all work. Right. Working along with everybody else that works in the electric company. You're going to be working until the lights are back on for everybody. And so it's an interesting industry in that on the one hand, it's pretty flexible, open. Okay, you can't steal from the company, but yeah, you can do a lot of things. A lot of these errand integration things that I mentioned, you tell your boss, yeah, I'm planning to stop by at the hardware store while I'm on my way out there, out to the substation. There'd be no problem. But on the other hand, if it's, hey, there's a lot of customers out of power right now, we need you to work on that and nothing else. And yeah, and my own family was left to fend for themselves. So that's kind of an interesting industry that way, but it does bring home how society counts on you. And when the lights are out, people want them on. Thank you. So let me go back to stop sharing. Here we go. And go back to the slide. Slide presentation. There we go. Okay. So let me pivot now and get into the more technical part of this discussion and talk a little bit about green energy. So what this slide illustrates is kind of customer demands. And it's utilities are franchises of the states they serve. And let me kind of deconstruct that a little bit. Most electricity in the United States is provided by investor-owned utilities. That's where I worked. That's Eversource. That's National Grid. Some of the electricity is provided by public power, and this is very popular in the northwestern U.S. There's an outfit called the Bonneville Power Administration. It's part of the federal government. They produce power, and they are the electric company in the Northwest to a large degree. Some is municipal power companies, so towns might have a power company. Like I remember Wallingford Electric in Connecticut. Wallingford, Connecticut was an electric company unto itself. But for the investor-owned utilities, the only way you're allowed to do business is because the state legislature where you serve has voted to allow you to be the franchise holder. So those electric companies are beholden to the government. And in return for the franchise, the government has a utility control commission that looks at every aspect of operations. All of this then is driven by customers. What the customers want is what the companies and the regulators are going to work to deliver. And so customers, this is what customers want here: cleaner environment, increased use of renewable sources, assistance in conserving energy. And that assistance in conserving energy is also really its interest in lowering the bills, right? If we can conserve energy, get all our stuff done, use less energy, that gets the electric bill down. So that's what people want. They want, first and foremost, they want the power to be there, and when they flip the switch, they want the light to come on. But that and safety, given that, these are the changes they're looking for. And so I thought we would take a look at electric system efficiency and see about where are some of the opportunities. And why would we look at efficiency? Well, because you can lower the customer cost. If you can operate more efficiently, you get everything, right? Lower emissions, reduced use of non-renewable fuels. It wasn't shown on that EIA, Energy Information Agency slide, but those renewable sources, in general, if they're available, that's what's getting used. So the nuclear plants, when they come on, they stay on. When the renewable plants come on, they stay on. And if something needs to modulate its output so that the total amount of electricity made is equal to the total amount consumed, that modulation is done with the older fossil plants. So those smokestack plants is who's changing their power output, but renewables are getting used. So let's take a look at some of the efficiency areas. And I thought I'd just deconstruct it a little bit for you. This is the system as it existed when I started in the industry about 1980 or so. And if you look on the left side, even up through 2015, that power plant cycle over there, it's called a simple cycle power generation. And what that means is that a fuel is burned, and it might, or the heat source might be nuclear, but there's a heat source. And what that power plant is doing is it's going to boil water. The water's going to spin a turbine. The steam is going to spin a turbine. The turbine's attached to a generator, right? It's a magnet and a coil. And that magnet and the coil is how you generate electricity, right? So there's a magnet and a coil, and then the water comes down to a condenser, which means we need to cool it off. And that might be those cooling towers, these big steamy cooling towers, so that it condenses back into water and we can run the cycle again. So then it will go back, it'll get heated again, and it'll get boiled again. Sounds pretty simple. As I mentioned, I worked at a power plant with 900 megawatts electric of output. We were boiling 6 million pounds of water an hour. So think about that, 6 million pounds of water an hour. I mean, what would 1 pound look like in a saucepan on the stove, right? Not small, not really big, 6 million an hour. So that was quite the cycle. Now in this system, again, it's burning something. So about 2/3 of the energy is going out the stack as waste heat, and 1/3's turning into electricity. And then there's that delivery system where we're pumping up the voltage for transmission, lowering it a bit for distribution. And that system operates at, on an average across the US, about 7% losses. And that gives us maybe at an end use 60 watts of electricity available to light an old incandescent light bulb. But the incandescent light bulb was only converting, 7 watts of the 60 into light, which is what we wanted, and 53 watts into heat. And I imagine you all have come across incandescent bulbs occasionally, right? And if you happen to try to unscrew them after they've been lit for a little while, you burn your hand. I mean, they're really hot. Look at those losses, 88%. And yet this was the typical system of 2015. And so let's move forward here. Fluorescent lighting has become really big, 75% more efficient than incandescent. So now, instead of 88% losses in the end use, or the light bulb in this case, but this is a proxy for any end use utilization. Here we have now just 52. Now, no one would brag about a system with 52% losses, but it's way better than 88% losses. Okay, but let's look at what happens now at the other end of this system. We had 190 watts of thermal power to get us 7 watts of light in the system, in the old system. With this, we only need 48 watts of thermal power. 190 became 48. So fluorescent was a big advance. Now, that said, of course, we've already moved on, haven't we, really, from fluorescence? And we're moving toward light emitting diodes, which is even more efficient. So much better still. So there's been a real change, and it's been happening lately on the end use end. Now let's look at the cycle at the power plants. Now this is where I wanted to take the question, Professor Mughal, that you mentioned. Why aren't we seeing the needle moving on renewable use, really? And my answer to you is two-part. One is there's an awful lot of installed generation already, and increments of solar that show up along the highway. They're notable, but they really don't move the needle. They're very small in comparison to those central generating plants. So you don't really see them move the needle on the renewables. Further, the way they're measured, that EIA, the way that's measured, it doesn't even measure the solar in a house that's behind the meter, right? They're getting data on what travels across the wires. So if a person puts in solar and uses the power at their house, they don't even see that in that computation. However, we are still using a steady amount of electricity, but the rate of growth of use in the US has really declined, and that's in part due to the adoption of end-use solar. Finally, let me make these points. I see that it's 3:40, and I want to leave time for questions. Underneath that EIA total of sources, there's been a real change. Petroleum has shrunk. Natural gas has grown. Coal has shrunk really low. Back when I started, coal was over half of all the power, like fuel for electricity. Now you saw it was well, 90% of the coal is going to electricity. It's a very small contributor to total electric fuel. What's replaced it is this combined cycle, and these tend to be a natural gas plant. And what's going on here is a combined cycle plant it's kind of like 2 bites at the apple being the heat available. So first there's a gas turbine cycle. So this is like a jet engine. Only in this case, instead of trying to push an airplane forward, the jet engine has, again, a shaft, and it's going to a magnet and a coil. We're making electricity, right? So that's the jet engine. But that jet engine exhaust is really hot. And so if we boil water and we run one of those simple cycles off the exhaust from the jet engine, we can convert a lot of that waste heat, about 1/3 of it, we'll get that as electricity as well. So that's why they call it a combined cycle, because the 2 cycles are going on. They're both about 1/3 efficient, 2/3 inefficient. But because we're putting them together, we're able to reduce the losses a lot. And remember, this was in the 40s of watts before. Now it's down in the 36 watts of thermal power, again, to get our 7 watts of light. And then to wrap this up, let's just look at the delivery system. Well, the delivery system was 7% already, but new federal efficiency standards were put in place back about the time I was leaving the industry, so around 2012. And these required that future electric distribution transformers be more efficient. Now, these transformers last 40 years each, and so it's going to be a long, long time before the new ones replace the fleet of existing transformers. But they are being replaced with more efficient, and so we're moving toward, instead of 7% losses, 6.8%. Worth doing, not a big mover. So there's real opportunities, I think, for electrical engineers, both in the power plant side, but really in the end use utilization side. I think there's more efficient devices, many opportunities there. And this is just a little summary. End use, we can get maybe 75% more efficient there, and we can get that near immediate. I say that near immediate because every time we throw away an incandescent bulb and replace it with an LED, that's the kind of improvement we're getting. Generation, that change is ongoing, Professor Mughal. It would show up not as renewable power, but it would show up as reduced greenhouse gas emissions. And there's been fantastic progress on that front in the electric industry. In fact, the electric industry has really flattened greenhouse gas emissions, enough so that for the state of Massachusetts, as compared to 1990, our greenhouse gas emissions are down by 25%. And I'll tell you what, all of that is from electric generation, converting to those combined cycle and using natural gas as a fuel instead of coal or oil. So to summarize, the power industry offers a great essential service. It is being modernized, so there's real opportunities for well-compensated careers. There are many more opportunities to help change the world and make it more efficient and sustainable. And with that, I'll stop sharing here. Oh, I had a slide there just to say thank you, and I'll just mention this. This has my contact information. So students, if at any time you want to, I work for WPI. We're here for you, the students. Feel free to ask any questions, write me an email. You can look at me on LinkedIn if you want to. And other than that, I'll stop sharing and take questions. Well, I think fusion's an exciting area, and I'm glad our government continues to fund research to keep pushing that forward. But I think the MIT announcement is about getting a self-sustaining reaction going. And if you think about fission reactors in nuclear, right, in the urgency to get a bomb to help win World War II, the US and allies developed nuclear technology over the course of about 4 or 5 years, right? The early work on radioactive piles and so forth was probably starts in 1930. So I think even with a self-sustaining fusion reaction going, we're decades away from converting that by engineering into a power plant. So that would be a heat source for power. I also think fusion is maybe a little oversold. And this is coming from someone who supports nuclear power. That's me, and I've worked in nuclear power for a good part of my career. But just as you get waste with fission reaction, and you get waste, what happens with fission is you break an atom and you get every atom that's smaller. They break apart and you get a probability distribution of all the smaller atoms in fission. And so some of those smaller atoms have very long half-lives, and they're radioactive for really long time. So there's a need to keep the waste isolated from the environment pretty much for 1,000 years. And so this is the challenge with the fission reactors. Well, fusion is not going to be problem-free. Well, fusion won't get that from breaking hydrogen atoms into hydrogen atoms that have an extra neutron into smaller hydrogen atoms. That's what fusion's doing. That's what the sun does. It still generates lots of other types of radiation that irradiates, which means that the materials around it become radioactive. That'll be a waste challenge. So I think it's encouraging that we're working on it. I think it's good that we keep working on it. I think any kind of commercialization, though, is decades away. And I do think it won't be problem-free. I never see the fusion people talk about what will be the quantity of radioactive waste they generate, because it won't be small. It'll be notable, just as it's pretty substantial at the nuclear power plants, fission power plants that we have now. Good question, though. Interesting.
So if you have to pick between nuclear and renewable energy technology, which one would you pick?
I'm sorry, Professor Mughal, you were saying?
If you have to pick between nuclear or renewable energy technology, which one would you pick?
Yeah, I don't think it's either or. I remember seeing a candidate before he was President Obama fielding this question, and he said all of the above. And I thought that was a great question because if you look at a system and how does a system operate, it helps to have large central station nuclear plants turning out a lot of power. So I like the idea of keep the ones we have. That said, they're hideously expensive. And so why would we build any more? Well, we're basically not very many more. But if the choice is that or a coal plant, I think that's good to build nuclear. At the same time, building out solar and wind and adding those in quantities, and as the learning curve comes along, we'll see we'll get more and more output per dollar out of these sources, is also worthwhile. So I tend to think all of the above.
Okay. Well, you're almost running out of time now. Thanks again for joining us. We really enjoyed it. Let's thank our speaker, folks.
Thank you.
Thank you so much.